I did expensive compression tests to compare the strength of different materials, wall thicknesses and printing technologies. To improve the performance of my thermoacoustic Stirling engine, I need high pressure resistant components and would like to test the limits of 3D printed parts. I've already used a lot of 3D printings in my engines. When airtightness was required, I printed with slightly overextrusion and treated the parts with epoxy resin. This method is somewhat effective, but impractical and messy. Now I have looked at how the professionals do it and asked the company Diamant, who sent me a few bottles of Dichtol to try out free of charge. I'm giving my honest opinion here. I was simply provided with a product free of charge and have no specifications about the content. In addition to the components for the thermoacoustic Stirling engine, I also designed and printed a lot of test samples. I used PLA, PETG and ASA materials and printed with wall thicknesses of 2 to 3 mm and 1 to 4 wall loops. I also experimented with different printing techniques, especially with regard to the Z-seam. I printed almost all of the parts using a 0.6 mm nozzle. My design of the first batch of pressure test pieces was rather impractical. The small inlet opening made it difficult to fill them with enough Dichtol. Dichtol AM contains solvents. If you don't like the smell, it is better to use the water-based Dichtol AM Hydro instead. With the test samples made of PETG with a wall thickness of 2 mm and only one wall loop, the layers tear open at 3 bar pressure. The ASA parts with thin wall thicknesses and a single wall layer exploded spectacularly at 4 bar. With 3 mm wall thickness and 3 wall loops, ASA bursts at 8 bar. PETG with 6 solid walls is stable up to 8.5 bars. Above this, it develops a small, permanent leak. I am very satisfied with these first results. With a solid printed wall thickness of 3 mm, pressures up to 10 bar are possible, making the use of 3D printed parts in the thermoacoustic Stirling engine perfectly reasonable. PETG had continued to prove itself as my favorite filament. Not only has it withstood the highest pressures without ever exploding, it always leaked in a controlled manner. The Dichtol fulfilled my expectations. Although the test pieces were not optimal for the treatment, the strength of the printed layers determined the compressive strength and not the sealant. The printing settings of the seams and similar in the slicer are no longer so important. Minor printing errors are reliably sealed by the Dichtol. I will now try out better test bodies and experiment with fiber-reinforced engineering filaments to see if they really offer better strength under compressive load. I will report on this in the next video. As always, I'm very happy for your suggestions, criticism and comments. Many thanks for watching.